Good day everyone. Today, we will explore Chapter 5, Internal Memory. In this chapter, we will learn about different types of semiconductor memories, their internal organization, error correction techniques, and advanced memory architectures like SDRAM, DDR, and flash memory. Semiconductor memory is broadly categorized into dynamic RAM, DRAM, and static RAM, SRAM. Each type has its own structure, advantages, and applications. Understanding these differences is key to appreciating how internal memory functions in computer systems. Dynamic RAM, or DRAM, stores data as electric charges in capacitors. Since these charges leak away over time, the data must be refreshed periodically. This is why it is called dynamic. DRAM is simple to manufacture and can be made very dense, making it ideal for main memory. Static RAM uses flip-flop circuits to store data, making it faster than DRAM. Unlike DRAM, it does not need refreshing as long as power is supplied. However, SRAM is less dense and more expensive, which is why it is typically used in cache memory rather than main memory. Let's compare SRAM and DRAM. Both are volatile, needing continuous power. DRAM is simpler and cheaper but slower, while SRAM is faster and used in caches. DRAM is preferred when high capacity is needed at a lower cost. Read-only memory, or ROM, contains permanent data that is wired during manufacturing. It does not require power to retain data. A key disadvantage is the inability to correct mistakes without discarding the entire batch. Programmable ROM offers more flexibility. Although it is non-volatile like ROM, it can be written to once after manufacturing using special equipment. PROM is ideal for large production runs where a degree of flexibility is needed. Read-mostly memory is optimized for reading operations. Although not much detailed information is presented here, in general, this type of memory allows infrequent updates and is useful for applications where data changes rarely. Interleaved memory improves performance by arranging memory banks to allow simultaneous access to different banks. This technique reduces access time and enhances memory throughput. Memory systems need mechanisms to correct errors. There are two types of errors, hard failures and soft errors. Hard failures are permanent defects, while soft errors are temporary disturbances that do not cause physical damage to the memory cells. Error correction increases the word length because additional bits are added to store parity or error detecting codes. This ensures higher data integrity but slightly reduces available storage for user data. With high-performance processors, the bottleneck often lies between the CPU and the main memory. To address this, enhanced DRAM architectures like SDRAM and DDR DRAM have been developed to speed up the memory interface. Synchronous DRAM, or SDRAM, is synchronized with the system clock. This synchronization allows it to deliver data at a much higher rate compared to traditional asynchronous DRAM. Double data rate DRAM, DDR DRAM, improves data transfer by sending data on both the rising and falling edges of the clock signal. DDR DRAM is widely used in modern computers due to its high speed and cost efficiency. Flash memory is a type of non-volatile memory widely used both internally and externally. Unlike traditional EEPROM, flash memory can erase blocks of memory simultaneously, making it faster and more efficient. Flash memory is crucial in devices like SSDs, USB drives, and memory cards. To summarize, we have explored the structure and operation of semiconductor memory, focusing on DRAM, SRAM, ROM types, error correction techniques, and advanced technologies like SDRAM, DDR, and flash memory. These technologies collectively form the backbone of modern computer systems' internal storage.